the course Mathematics of Generative Modeling, and we were doing sequence models. So in sequence models, the data we have is in a sequence, and we are supposed to predict next in the sequence. So in this case, the problem is defined as, so we are given, let us say, these conditionals. So we are given a sequence x1, x2 up to xt minus 1, and from there we want to learn a probability distribution from where we can sample xt. Okay, so we can model the problem like this. So one of the initial ideas on this would be the guys working on time series model. So they are also ordering is sequence of data or the time series data is required. So so it's time series data is also a sequence, is also can be considered as a sequence. So in this case, then we can look into let's say a well-studied framework which is autoregressive models. So we have seen this in the last class. So we can start with this initial intuition of autoregressive models, and here as well we may start with a very basic, which is linear and first order, and then we can generalize this, let us say, okay, to nonlinear, higher order, and so on. So we will see. In fact, we won't go into too much of these classical so-called ARP methods. Rather, we will jump into neural autoregressive and let it generalize via nonlinearities and so on. So, but it is a good idea that we look into at least the basic linear first order case. Okay, so that will be the plan, and so we can define define a linear auto regressive models as a recurrence. So it's a recurrence we can define. So first of all, we take a noise parameter, white noise. So let us say this is with mean 0 and variance sigma square, and then we define the stacked sequence data as T1. So basically here we are looking into x, which is of the form, let's say x1, x2, xt, where xi's are one-dimensional. Okay, so this one corresponds to the fact that each of the data in the sequence is one-dimensional, and t here refers to the time. Okay, let's say this ordering 1, 2, 3 up to t, and this is the ordering we fixed. So this is essentially a time series problem, and in this case the data is one-dimensional, and we have this noise process, white noise process, and that will be part of the model. And the sequences at time t are defined as follows. So I can define it here. So xt is rho xt minus 1 minus mu plus epsilon t, and x1, the first in the sequence, is mu plus epsilon naught. So this is the recurrence for linear autoregressive, and this is the first order because it only depends on the immediate previous one. Okay, so this is the AR1, and in fact, as you can see, we have assumed a Markov property. So we have assumed Markov. So all this we have also seen in the previous class, but then I will kind of do this quickly, recall this, and then we will continue with what we want to do. So what we expect is that this data xt is related to previous data like that. In this case, it's just on the previous xt minus 1, and what we expect is that this data xt that is being generated, it follows let's say some these are samples following, let's say, normal distribution, which is one of the popular models to use. So in this case, what we expect is that xt given x less than t. Remember that this is what we want to know. Okay, in this model, we want to learn the probability density of xt given. I have seen all the previous data in the sequence. So in this case, we have normal. We assume our model to be parameterized by the normal distribution. So that's why we choose normal, and then xt minus 1 minus mu plus mu plus sigma squared. And obviously our goal will be to learn rho, which is not which is the parameter of our model. And and the last one will be not plus, but it's a variance, so it's a sigma square. Okay, so we have shown before that expectation of xt is mu for all t. So this implies that this is a process with a stationary mean. So this is a autoregressive process with stationary mean, meaning mean is constant. And then we later defined stationary pth moment. So we can see this also as a first order moment about, let's say, 0. Okay, and then we have also defined a stationary pth moment when we have xdp is constant. Then we call it x as a time series x as a stationary pth, has a stationary pth moment. Okay, so and then if we have to let us say estimate mu, so in this what we have in hand in the normal distribution you can think of is this quantity. Okay, and the data is given to us, which are x1, x2, x3 up to xt. Okay, and in our model we have these parameters that we don't know. Okay, so this is like rho and mu and so on. Okay, so one possibility is that we, as usual, what we do is that we estimate the mean given the samples we have. So let us say in this case the samples we have are x1, x2, dot dot dot, xt, and so on. Then one possibility is that so let us say in this case the x1 came x1 has mean mu. Okay, but we don't know what exactly is that because we don't know the distribution of x1. Okay, we know x1, but we don't know the distribution of x1. So hence we don't know mu. So one of the possibilities is that we do sample mean as an approximation. Okay, that's what we do usually. So we take a lot of these x and then we take a average, okay, arithmetic mean of these. So this is something we have also seen in the last class, but then we saw that this arithmetic mean is not a unbiased estimator of the true mean, and we used law of large numbers. And when we use law of large numbers, we when we look into the Chebyshev inequality, then we saw that the variance term may not it does go to 0 when we have IID case, but in this case we don't necessarily have IID. So then we derived some expressions in the last class, and this expression was derived in the case when the time series data is wide sense stationary. Okay, so to put things in context, I will put those definitions and the result that we stopped last time. Okay, so continuing, then what we have written in the last class is we define something called time series x is wide sense stationary. So this is wide sense stationary when we defined that covariance of xt minus k is equal to covariance of xs minus k, and this is true for all s, t, k natural number. Okay, this is how we define wide sense stationary, and in this case we also define autocovariance function gamma that goes from natural number to real, and in this case we defined autocovariance to be covariance of xk plus 1 x1. Okay, so we have defined all this, and as you can see from the result here that we can kind of write this as so basically if I look here, then I'm allowed to change the indices, increase the indices and so on, and then I can essentially write it in the form of one of these, and then I can change the indices to any of the t or s, and we can have that gamma k is equal to many different forms. Okay, so so for the moment we leave it until here. And so what we did in the last class again is that we defined the sample mean mu hat to be 1 over t, and this was sum of xt and t equals 1 to capital T. Okay, and we said that is no longer a an unbiased, I mean, because xi's are not necessarily IID, so we may not claim that this is an unbiased estimator of the true mean. But then from our analysis in the last class, what we derived is that we looked at the variance of so what we looked at is the Chebyshev inequality, which is mu hat minus mu greater than equal to delta is less than equal to variance of mu hat by delta square basically. Okay, so this is the Chebyshev inequality, and when xi's are IID, then the variance goes to 0 as t tends to infinity, and then we do get that mu hat is a it gets pretty close to mu, or it becomes even a unbiased estimator of the true mean. But then in this case we are not sure whether the variance of mu hat will go to 0. So to work a little bit on this, where we want to know what exactly variance of mu hat is, let us say in this specific case, because in general we cannot say anything, but let us say in this specific case where the time series data is white and stationary, then can we have this quantity going to 0, and if yes, then what are those conditions under which it will. So continuing, then what we wrote in the last class is that we derived that variance of mu hat is less than equal to gamma 0 divided by t plus 2 by t sum of gamma k and k equal 1 to t. So this is what we derived in the last class, if gamma 0 is some finite quantity, then we know that the first term will go to 0 as t tends to infinity, but we are not yet sure about this sum of gamma k term. So if sum of gamma k term does not sum to some finite number, then we don't have the variance mu hat going to 0. So hence everything now depends on whether gamma k is summable or not. So hence our analysis goes in that direction now, and we continue from where we left. So if indeed if gamma k is summable, so if gamma k is summable, then indeed variance of mu hat will be order of 1 over t, which means that it will go to 0. So this has a inwards, this means that faster a process forgets its history as measured by the autocovariance faster the sample mean mu hat converges in distribution to mu, converges in distribution to the true mean mu. This is how we interpret this. So now everything now depends on whether gamma k is a summable function or not. In other words, the sum of gamma k from k equal 1 to infinity is bounded, because if k equal 1 to infinity is bounded, then any partial sum of this also will remain bounded. So and this will be, let us say, in a specific case where we have time series which is White and stationary. Of course, in general we cannot make such claims. So so moving forward, our focus will be on expression, deriving an expression for gamma k when xt is a White and stationary. So some of the results that we may have as a auxiliary result is the following. So continuing, the way we have defined AR1 process in our notations is it is xt is the row of xt minus 1 minus mu plus epsilon t. So you will see this xt defined in different way in different books. So this is how we prefer to define it, and it starts with x1 being mu plus epsilon naught. So this is the autoregressive process we have, and where epsilon t comes from normal with 0 and sigma square mean, which is the white noise we have. Okay, so what are the properties we can have? So let us see if we compute the variance of xt. So if we look into the variance of xt, so variance of xt which is denoted by var of xt. Now this will be the variance of this guy. So this is variance of rho xt minus 1 minus mu plus epsilon t. Now this will be equal to, now variance in a variance constant terms drop. So basically variance of a plus x is variance of x, and variance of x plus y, if x and y are independent, is variance x plus variance of y. So these are the two results that we may use. So in this case, where we have that we will, if we solve for this, then this will go away, and we have this variance of this guy. So this is like variance of rho xt minus 1 minus mu, and then plus variance of epsilon t. Okay, so we have that xt minus 1 minus mu and epsilon t are independent, and hence we can do this splitting. And then in other words, we can also say like covariance of xt minus 1 and epsilon t is 0. So in this case, then again rho can come out, because we have another result for the variance is that ax is a square variance of x. So if we do that, then in this case rho square comes out, and we have variance of xt minus 1, and then mu goes away from the first property, and then plus variance of epsilon t was sigma square. So this is the relationship we have between variance of xt and sigma square. So one of the things we would like to know is whether the variance of xt becomes stationary at some point. Okay, so what if I keep doing this recursion, then is it that the variance of xt will settle down to some constant variance? So in this case, we may run this recurrence and then see what we get. So for instance, we can continue this recurrence again and again, and then we can try to see where does this settles down. So this is rho squared, and in place of variance we can do this recursively now. So variance of xt minus 1 will be rho squared variance of xt minus 2 plus sigma squared plus sigma squared. Okay, so this is what we have, and we can remove this, then we don't need this. So this is what we have, and then from there what we see is what we get in the process is rho to the 4 variance of xt minus 2 plus rho squared sigma squared plus sigma squared. So from here kind of we can keep doing this recursively, and then we may kind of try to see where does it end. So let us see this. So if we continue this process, then what we understand from here is that we will get a sequence, and what also if we look at this row, and if this row kind of tends to 0, then eventually these terms asymptotically will the leading terms will vanish basically. Okay, so if we for t large enough, so what we will get in process is that we will have sigma squared, and then we will have 1 plus rho squared plus rho to the 4 plus dot dot dot. Okay, and then if t is very large, then the last term will be kind of almost 0 basically. Okay, so so in this case, then we can say that this is of the form sigma square, and this is a geometric sum. So this is times 1 by 1 minus the common term, I mean the factor, and hence the variance of xt will settle down to sigma square divided by 1 minus rho squared. So hence we can say that the time series xt, hence time series xt is has stationary variance. So we can make a claim that it has stationary variance. So this is the first result, and what we can also, what is really what we are really looking for is an expression for, if you recall, the bound that we had before is the expression for gamma k, which is the autocovariance, and we may do this as a next step and see derive an expression for gamma k. So to derive an expression for gamma k, okay. So continuing, now we will go ahead and try to find an expression for gamma k, and what we have is that we have already written expressions for these xt and x1. What we'll do for simplicity is that we will subtract the mean from each of these, let's say. So then we will make it a zero mean process. So let us say we define yt, which is xt minus mu. So this would be rho x t minus 1 minus mu. So our xt is rho xt minus 1 minus mu, and then plus only plus epsilon t, because the mu gets cancelled now. This is plus epsilon t. Okay, so we define a new yt, which makes it a zero mean, which is a zero mean process, and then gamma k will be can also be written now as a covariance of y k plus 1 y1. Okay, so our gamma k now becomes yk plus 1 y1, and we can go ahead and now compute this expression gamma k. So let us do it here. So let us compute gamma k. So gamma k is covariance of y k plus 1 y1. So now we put the expressions for y. So if we look into the y expression, then this is covariance of rho. So this is covariance of rho times yk. So this is rho times yk, and then plus epsilon k plus 1, and then we keep the y1. Okay, so we use the expression there. So yk plus 1 is rho. So basically this could be seen as y t minus 1. Okay, so that's what we did here. So we write yk plus 1 as rho of y k, and then plus epsilon k plus 1, and then we are taking covariance with y1. So here is our y1, and now we use the covariance property, and we are allowed to split this. So this is covariance of rho yk y1 plus covariance of epsilon k plus 1 y1. So so this guy will go to 0, and then what is left is that we take the rho here, and then this is covariance of yk y1, and this is rho of this is basically recursively this is gamma k minus 1. So what we get is a recurrence, okay, and in this recurrence we suspect that the solution of this so here we have made some assumption here where k greater than equal to 1, because there will be epsilon as well here, and we get some Dirac delta function, and then for I believe k greater than equal to 1 that eventually does will go to 0. Okay, so there is something to fill here, and here we want to see that whether what is the solution of this. So we suspect that the solution of this will be solution of this recurrence. So solution of this recurrence will be let us say rho k gamma 0, rho k gamma 0. So if we put this recurrence here, then we can check that this indeed satisfies this. So here gamma k is rho k gamma 0, and here is rho times, so this recurrence is satisfied, so rho k gamma 0, and then if we look into the right hand side, then we have rho and gamma k minus 1. So gamma k minus 1 is rho k minus 1 gamma 0. So this is also rho k gamma 0, and the starting value of gamma k is gamma 0. Okay, so the starting one is indeed gamma 0. Okay, for k equals to 0. So this solution makes sense. Okay, so this is the solution of this recurrence, and now remember that we want to find an expression for the gamma k. Okay, and I've left this a little bit as an exercise. You expand this more, then you will have some epsilon 1 term, I believe, and then you will have covariance between epsilon k plus 1 epsilon 1, and then you have you can write this as a Dirac delta when k plus 1 is equal to 1. In other words, yeah, so k plus 1 and 1, so then it will depend on the difference between them. So basically when k is 0, then that will be 0. So in our case k is greater than equal to 1, and that certainly makes this 0. Okay, so I'll leave this part as an exercise. So so continuing that, this recurrence we have this rho to the k gamma 0, and basically, yeah, now we so basically to find an expression for gamma k, we need to know what was gamma 0. Okay, so gamma 0 is essentially the variance, okay, the variance of x, but the variance we have already computed. This is sigma square divided by 1 minus 1 minus rho squared. So if we substitute that, then you can verify that it will be sigma squared divided by 1 minus rho squared as a solution of this. And then again, if rho is less than 1, then if this is a summable quantity, okay, so and right, so and then obviously we have also assumed that this is a White-Sense stationary process, which I leave this as an exercise for you to show that that this indeed follows a White-Sense stationary. But my point was to kind of derive an expression for this, and if we have this, then the idea that this is summable essentially is dependent on whether this guy is summable. So here these guys are constant. So basically gamma k being summable, essentially it boils down to the rho k being summable. So if I so so we were looking for in the bound sum of gamma k, k equals 1 to t, and so on. As t tends to infinity, we were for as t tends to infinity, we want to know whether it's summable or not. So this boils down to basically the constants come out, rho square by 1 minus sigma square, and this is rho k, k equal 1 to infinity. So this is basically a power series, and if the rho is less than 1, okay, if the mod of this rho is less than 1, then we so this will be less than infinity if the rho is less than 1. So for our bound, what we have is it is summable for white sense stationary process, and then in that case we do have that as t tends to infinity, because t we had in the bound, if you look at again, we had this variance of mu hat is less than equal to gamma 0 by t plus 2 by t, and then sum of gamma k, and k equals 1 to t. So we were worried about this term. Now this is the rho being the absolute value of rho being less than 1, and if this gamma k is summable, then this will end up as a finite quantity, and then overall this will go to 0 as t tends to infinity, and from there we can claim that probability that mu hat minus mu greater than delta is less than equal to variance of mu hat by delta square. So this guy will then go to 0, then mu hat is a good estimator for the true mean. So so the regression parameters, basically the rho that we have, that plays a role. Okay, whether our sample mean will be if we choose our sample mean in that way, then there are constraints on the regression parameter. Now another question is the regression parameter themselves need to be found out. So how should we find out the regression parameter? So let us see this as a next step. If so we have that we are using a normal distribution for this process. We fit a normal distribution, and hence to fit our model with the parameter rho, we would like to maximize the likelihood. So let us define the likelihood function, and in fact a log likelihood, and try to maximize. So if you recall, we have that in our model, what we assumed is the following, is that the probability distribution of xt given x less than t is normal, and rho xt minus 1 minus mu plus mu sigma square. And so this is our template. This is the normal distribution we want to fit, and here there are quantities like mu, rho, all this needs to be found out, and sigma also. Okay, so so one of the things that we have seen previously is that we can estimate the mu of our model using sample mean. Okay, but we have to be careful that the regression parameters are less than 1. But if it is the case that regression parameters are less than 1, then it seems that sample mean will be a good estimator of the true mean. Another thing that we would like to describe is or compute is regression parameter rho. So from this model, if we look into this, then we will kind of write the expression for the normal distribution. So recall, the expression for the normal distribution will be given by, recall, so this is the multivariate one. And then this will be L of, let us say, we pose this as a problem of rho, the regression parameter, as a variable, let's say. So then this will be I equal 1 to n, and then 1 by square root of 2 pi sigma squared, and then exponential of xt minus rho xt minus 1, and then minus mu, and then whole thing minus mu, and then basically whole thing squared also. So this is squared, and then divided by, so we can make a space for to put a negative as well. So this is exponential of, and this is minus 1 over 2 sigma squared, and this is, so this is what we have for the multivariate normal. And our objective here is that we would like to kind of maximize the likelihood function, or since it's a normal distribution, so working with log will be good because it will cancel out the exponential. And so let us go ahead and try to define the log likelihood. So in this case, log of L rho is minus n by 2 log of 2 pi sigma squared minus 1 by 2 sigma squared sum of xt minus mu whole squared, or I will write it in more cleaner way. So this is xt minus rho xt minus 1 minus mu whole squared, and this is t equals 2 to n. We have taken a log, and when we take a log, then we have this term given by this, and then the log of the second term is given by this. And then we want to kind of maximize this, and remember that this product is taken over t, so I think I should use a t here. We are taking this over x1, x2, x3, and so on. So t equals to 1, then we have certain expression here, and then for t equals to 2, we have certain expressions, t equals 3, and so on. And these distributions that we are getting for different t's, we are assuming that to be independent. Okay, in our model, we are assuming that that these are independent. So xt plus 1 given up to xt given up to xt minus 1, and so on. So that's why you see this product here. Okay, so there is underlying assumptions that these probability distributions p xt given x less than t are independent in our model. Okay, so we may not have proved it, but this is an assumptions we have in our model, and hence the joint probability of this will be the product of the probabilities for each of these x1, x2, x3. Okay, so basically we want to find the regression coefficient rho over this each of these samples x1, x2, x3. x1 is already given, so let's say x2, we start from x2, let's say. So x2, x3, x4, x2 we get some normal distribution, x3 we get some normal distribution, and for certain rho. Okay, and x4 we get some normal distribution for certain rho. Okay, in this case, in this row, okay, which is fixed, and then x3 we get a row, and so on. So we are saying is that this row that we have, which is a parameter in our model, this should be such that the joint probability, which will be in this case is the product of the individual PDF because of the independence, and that should be maximized. The probability should get maximized, right? So that's how the maximum likelihood estimates work. So in this case, that's what we did. These products are being taken. Okay, so you could use 2 here. So these products are being taken, and then usual norm is that take a log likelihood, and we take a log, and then now we want to find our optimal row. So maximizing the likelihood or the log likelihood is okay, the point where which I will find a maxima for the log, but the same point at which we'll find a maxima for the L, because log being a monotonic increasing function, it will not change the point where I will get the optima for rho. So hence log is convenient. Now to maximize this, I will take the derivative of this log likelihood and equate to 0, and if I do that, then from there I will get an optimal value of rho. So let us do that. So if we take the derivative with respect to rho and equate it to 0, then what we will get is the following. So we can write down one more line just for the sake of note. So we want to maximize log L rho, which is the log likelihood or MLE estimate that we are doing here. So if we see the first term, there is no dependence on the rho, so derivative with respect to rho goes away, and so on. So to maximize this, we use calculus, we take the derivative and equate to 0. So we take the derivative with respect to rho and equate to 0. So this is something we recall from calculus, that if I have to find a minima of a function, then I look for the point where the tangent becomes flat, and that gives me maxima. So that's why we take derivative and equate to 0, because at the point of minima, the gradient should be flat. Okay. Obviously, there are a few more details, that it is a convex function and so on. Okay, that we assume here that it's convex in rho. Or in case of maxima also is the same story, with whether it's maxima or minima. In this case it's maxima, so we also at maxima it will be flat. Okay, so all those are underlying detail for the optimization there, but while maximizing this, we take the derivative equal to 0, and we hope that that point at which the gradient becomes flat is indeed the maxima. Okay, and that will be guaranteed if it's a convex. If it's a concave function, then that will be a unique point. So where maxima is achieved. So then continuing, we take derivative and equate to 0. So then what we have is the d log L rho divided by d rho, and after taking derivative, you can check these things. I'll just write down from the notes. Okay, it's easy. And t equals 2 to n xt minus mu xt minus 1 minus mu minus 2 rho 1 by 2 sigma squared xt minus 1 minus mu whole square t equals 2 to n. So we took the derivative and we have to equate it to 0. Now derivative you can check, as I said, first term there will be no contribution, but then there will be contribution from the second term, because rho is lying there. So then you can kind of square the term, square those terms. So for your benefit, I can kind of do this additional expansion so that you can check this. Log of 2 pi sigma squared minus 1 by 2 sigma squared sum of x t minus mu squared and t equals 2 to n, and then plus 2 rho 1 by sigma squared and sum of xt minus mu and xt minus 1 minus mu minus rho squared 1 by 2 sigma squared and sum of xt minus 1 minus mu whole square t equals 2 to n. So I have done this expansion for you, the inner term, and you can see this a minus b whole square form, where a is taken to be this quantity and b is taken to be this quantity. So a minus b whole square form, I have just expanded that, and there will be no contribution from the first term because there is no rho here. So this guy has no rho here, this guy has no rho here. Okay, so no rho terms. So as you can see, when I take the derivative, these will go away, and hence the derivative will come only from the third and the fourth term there. So from there you can easily check that this is the case. So if we take the derivative, then we have we have this. So if we look there, then we have 2 rho 1 by 2 sigma square, and then xt minus 1 minus mu whole square. That's fine. And then here also, if I take the derivative, then I will be left with basically some will remain intact, and then I will be left with just the rho by, I mean not the rho will get cancelled, so I will be left with 2 by sigma squared. Okay, so I will be left with, right, so there is 2, and there is 1 by 2 as well, right? So there was this 2 here as well, there was this 2 sigma square here, so those kind of get cancelled here. 2 gets cancelled. So this is where we are, and we are supposed to solve for the rho. If I solve for the rho, now it is kind of straightforward that if I solve for the rho, then this implies that rho is sum of t equals 2 to n, and then xt minus mu, and then xt minus 1 minus mu divided by xt minus 1 minus mu whole squared. So this is our rho. Okay, so this is the maximum likelihood estimate for rho. Okay, so what we have seen here is that the parameters of our model are, I mean, sigma square, we don't have to do anything because sigma square is essentially the same sigma square that we sample from. This is the white noise, and this is something we know, let's say. Okay, so you can fix sigma square. Then we are left with estimating mu and rho. Mu, we can use the sample mean that we described before. So basically we can have the sample mean computed from the samples xt's, and then the autoregression parameter rho could be computed as an MLE estimate, having found let's say, having estimated the mean, let's say. Okay, so this is how kind of we can do the estimation of the parameters in the linear autoregressive case. My coverage of this is not very complete, I know that, and for more details on this, I just wanted to give you a basic idea. So for more on this, a course on time series, if I'm correct, or let me check the reference correctly. So to know more about this, it's good to kind of refer the document, a course in time series, and this is by Suhasini Rao, okay, the author, and this is a kind of a technical report, but I believe there is a book as well. So to know more about this, you can refer to this book, A Course in Time Series Analysis. The reason why I am not going into the detail of this is for generative modeling there are more powerful architectures. The basic intuition and ideas could be learned from this regressive model, which are the very basic one, and then again there is an extension to this, which is autoregressive P, and then in that case you look into P previous terms. Okay, so there is obviously a lot of things, and this whole book is about those models, and you can, if you are interested, you can go there. But our goal is to go into generative model case where this recurrence itself will be kind of parameterized with the help of neural networks. Okay, so we will see more precisely what we will do with respect to the neural networks. In fact, we will start with something called sigmoid belief network, or fully visible sigmoid belief network, and then we will kind of introduce a very simple variant of neural network with sigmoid activation functions and so on, and that will be our next step to extend these ideas. And then we will see even more sophisticated variant. Okay, the modern day ones are very, very sophisticated. You have RNNs, LSTM, and transformers. So this can also be employed for sequence model. In our case, we will be interested in the generation problem, and we will see how we will adapt that. But this forms the basis of kind of a simplest model we think of. But then here, the way you parameterized, or you're trying to fit the data via normal distribution parameters, and then a natural question is, can you introduce a different parameterization of these? Okay, so in sigmoid belief network, we will see how we can we can predict the parameters of the distribution distribution of our model. So if I have, let us say, Bernoulli process, and the parameter of the Bernoulli process is P, this is exactly what I don't know. The P is something I want to know. I have decided that the sequence data that I am generating, so let us say for the Bernoulli case, it will be the case of 0, 1, 0, 0, 1, 0, 0, okay, something like that. This is our sequence. So basically, you can say it's the heads or tail, heads or tail. The process that is generating this heads or tail is something you are trying to learn, okay, because in general, it may not be purely, let's say, unbiased process. So it may be a process which is not necessarily giving you 50-50, but it's a process that may be aligned more towards, let's say, head compared to the tail. So then we may want to estimate this sequence generation process. So then we can say, let us say this is, since this produces only two outputs, heads or tailed, pass or fail, success or failure. So these kind of problems are modeled by Bernoulli. And so hence, by looking at the data like this, which are in the form of 0, 1, 0, 1, 0, 1, it's natural to assume that that you go with something called Bernoulli. And Bernoulli has parameter P. And hence, we would like to say that let us fit this Bernoulli distribution for this data. Given this data, what could be the Bernoulli distribution? And asking what could be the Bernoulli distribution is the same thing as asking what could be the P. Okay, Bernoulli distribution only has one parameter P. So in that case, the sigmoid belief network, what it does is that obviously this is a prediction problem, and the data you have is x1, x2, xt, and so on. So the sigmoid belief network essentially parameterizes this by a sigmoid, and then you have some, let us say, combination of these data in further, let us say some f further of these data x1, x2, xt. Okay, so so this and this f itself can be parameterized by some parametric function. Okay, so in a sigmoid belief network, you now then you may want to do a, let us say, an estimate of this, build a loss function based on this, and then based on the loss function and the supervised data, you may try to find an optimal theta that learns how to predict P. Okay, so that's when you will learn this distribution, and then once you learn this distribution, then you know how to generate next number in the sequence. So this is sigmoid belief network, and we see this in the next class. Okay, so the idea here kind of extend from what we are doing right now. So we started with a time series, and then what we have in this case, our modeling assumptions is that probability xt given what I have seen up to t is a normal distribution. Okay, so that's our modeling assumption. Okay, that we assume that normal distribution will be a good template to work with, and then we have some parameters like rho and mu to be estimated. And then in this case, where you have binary data and so on, then I thought about Bernoulli distribution with parameter p, and then again, but then in this case, my p is now predicted by some small, let's say, neural network. Okay, and so that's how we will extend. That's how we will extend and build on this. Okay, so can we kind of use more and more complicated prediction functions and so on. So as we will see, we will gradually move towards RNN, LSTM, and so on. There will be changes also in the architecture that we look at. So what kind of architecture we are looking at? Okay, so is it a shared parameter network, for instance? Okay, if I am indeed using a neural network, then what type of neural network I'm going to use? Okay, the neural network also comes in many variants. For instance, these are 3 different variants. Even if we restrict ourselves to sequential networks which are developed for sequential, even here there are variants. So we will look into these different variants and which of these are more suitable. But the current trend is with the transformers, which seem to be doing very well on more complicated prediction tasks because of some interesting features it has, which we will study in detail later on. And we will also look into RNN, LSTM, and so on. So this is what we have. So So as I said, this AR process we have discussed is AR1. So I can just define without going into detail ARP process. So ARP process will be defined in a similar way, but the recursion that we will use will be rho k xt minus 1 minus mu plus mu plus epsilon t, and k equals 1 to p, and then x1 is mu plus epsilon naught. So as you can see, the changes we have is that now we have a sum for k equal 1 to p, okay, small p, and that's why it's called ARP. Okay. Now I'm looking into p previous window, p previous sequences, and based on that, then now I estimate the parameter xt. Okay, and all these things, all these modeling assumptions are interesting. Okay, because there in the previous one, AR1, what we have is a Markov assumptions like this. So xt plus 1 is written in terms of xt and so on. But here we have more generic assumption here. So for instance, we have xt plus 1 is now looking into all these previous ones as well. Okay, all these previous ones. So there are kind of decisions kind of one has to make, because if you look into the later one, then you have to you have more computational cost involved, because you have now to compute just xt plus 1, now you have to look into all previous p sequences, I mean the words in the sequence. Okay, so these are this trade-off that one has to decide, and in fact these are the things which will also play a role here when we look into these newer architectures like RNN, LSTM, or transformers, where the like how much we look into the previous sequences, that also kind of determines the variations in the architectures of RNN, LSTM, or transformer. Okay, so this will become in some sense a hyperparameter. Okay, so this will be for the sequence. Okay, so with this I will stop.